All right, welcome everyone. We heard all about AI in the last section, and we heard from Secretary Wright how AI can be used for things like materials discovery. I'm Jeff Snyder, Program Director at ARPA-E, and also a materials scientist specializing in materials discovery. And I would like to talk to you about what an ultra-strong magnet can do for energy. So magnets are important for many applications. We know them in consumer electronics and memory storage, but they're also important for energy applications, such as transforming the electricity that we're using right now. But magnets are also essential for electrical energy generation and use. For example, an electrical power plant takes the mechanical energy from a spinning wheel of magnets and converts that into electrical energy. And 40% of all of the electricity that we produce is used by motors. Motors convert electrical energy back into mechanical energy, also using a spinning wheel of magnets. The problem is, we're going to need a lot more electricity in the future. And big power plants require big generators. A 10 megawatt generator, for example, can be up to 500 tons. This is very expensive to build and ship. And sometimes it can be even too big to transport. Sometimes that limits the size of the power plant that we can build. The solution is better magnets to make smaller generators for plentiful, cheap, reliable electricity for all. Now, there are two types of magnets, electromagnets and permanent magnets. An electromagnet uses an electrical current to produce the magnetic field. That requires energy. And it also uses copper wires, which are expensive, as well as large and heavy. In contrast, a permanent magnet uses the natural magnetic field from a ferromagnet to produce the large magnetic field. Now that's limited by the type of magnet, but not the volume of the magnet. So in general, it can be smaller and lighter than an electromagnet. That means we can make smaller, lighter, and more efficient generators and motors. That 10 megawatt generator is now only 320 tons when we use permanent magnets. Also, for motors, permanent magnet motor is about 1/3 the less size and weight of an electromagnet motor. And because it doesn't contain coils of wire to produce the magnetic field, there are less energy losses, and so it's more efficient, meaning it also uses less cooling. Now, how can we make this even better, you say? Well, an even stronger, ultra-strong permanent magnet would further reduce the size, weight, and cost for both generators and motors. Here's a comparison of cost for the various types of electricity that's generated. Since most use these magnetic generators, they will all benefit from ultra-strong magnetic generators, reducing their cost. And this is particularly important for the lowest cost energy today, where most of the cost is just that generator. So the lowest cost electricity in the future would be that made by ultra-strong magnet generators. They will also produce smaller, lighter, and more efficient motors for the highest performance vehicles. But again, this is important mostly for transportation where the weight and size of the motor limits the range and capacity. That's electric aviation. So ultra-strong magnets will enable the future of transportation. So in order to explain what we mean by a strong magnet, let's discuss how a magnet in a big wheel pushes electrons the way a water wheel pushes water upstream. The size of the magnetic field B is proportional to the amount of the push, like the size of a paddle. So a stronger magnetic field means that we can use a smaller wheel. A motor is like a generator working in reverse, where the natural flow of electrons pushes the magnet paddles around the same way water flowing downstream will push a water wheel. Now, the strength of a magnet also depends on its coercivity. And that's because the electrons push back against our magnet paddles, the same way water pushes back against a kayak paddle, trying to force it to bend. A magnet is only as strong as the coercive field HC, beyond which the magnet will bend. So the magnetic strength is characterized by the product of B times HC, which we call BH max. Here's a plot of BH max over the last century. You see, most of the materials that we use for magnets today, like electrical steel and ferrite, are iron-based materials with very simple structures. They have moderate magnetic performance. But then in 1980, an entirely new material was discovered almost accidentally. It has layers of iron, but then also a layer of neodymium and boron with a very complex structure, which is great for the coercivity. Now, this material has huge performance, more than 4 times that of ferrite and electrical steel. And so because of that, it now dominates 2/3 of the magnet market, mostly for high-performance applications. And this is all despite the added concern and cost of the rare earth element neodymium. But this shows the importance of a strong magnet. Now at ARPA-E, we hope to discover the next generation of magnet, which hasn't happened in 40 years, and double the BH max value. And we think we can do this using AI-powered computational materials discovery that allow us to discover materials even without making them in the laboratory. So for example, in 2023, Google DeepMind published in Nature 2 million new materials. That dwarfs all of the known materials we've had before that. Many of these materials have complex structures with 3 or more elements, just like neodymium, iron, boron. However, most of these materials won't be magnetic. To solve that problem, we can also take advantage of computational physics, where we can calculate the magnetic properties of a material just by knowing its structure. So Microsoft has done this by doing a search for new materials and targeting high magnetic strength. They target the magnetic strength of the best known magnets today. And they reported in Nature just this year that they found 140 new magnets, some of which have a magnetic strength even higher than any known material. However, these 2 materials have not yet been synthesized, and they may not even be stable. So at ARPA-E, we have a teaming strategy to put all this together. We will not only have the AI and machine learning for materials discovery, but also include computational physics to calculate the properties before we even have to make them in the laboratory. But then we will also include chemists who can help with the materials discovery, but also with the synthesis and characterization to make sure that the new materials are stable. And then finally, we will include microstructure engineering and application engineering to make sure that we can process this new material at scale for wide-scale applications. So, what will you do when ARPA-E invents a new magnet, other than generators and motors? Maybe you would design magnetically levitated vehicles or use them in fusion power reactors. Or maybe you might make compact power transformers or non-contact magnet gears. Or maybe you would start with beachhead markets, such as medical equipment or high-performance electronics. Maybe small motors for drones and lightweight airplanes. Or maybe you would come up with something more imaginative, like this magnetic spring that I have here. So, if you're interested in talking about materials discovery, new magnets, or whatever, come talk to me tomorrow morning at coffee. Thank you. And now I'd like to hand over the mic to Laurent, who will be discussing another super materials idea.
Thank you, Jeff. Hi, everyone. My name is Laurent Pilon. I'm Associate Director for Technology and Program Director at ARPA-E. Superconductivity is one of the holy grails of energy technologies. Superconductors can carry very high current without any resistance when they are cooled down below their critical temperature Tc. So we could do a lot of things with these materials. Imagine transmission lines delivering electricity around the country without any loss. As you may also know, passing a current through a conductor generates a magnetic field. But because superconductors can carry very high current, they can generate very high magnetic field, the kind that we need to confine the plasma in a fusion reactor. In the late 1980s, scientists discovered rare earth barium copper oxide of REBCO as being superconducting at temperatures below 100 Kelvin. Before that, we thought that superconductivity could be observed only below 30 Kelvin. So now we had a superconducting materials at the temperatures of liquid nitrogen. Since engineers and scientists have found ways to make REBCO in the form of tape. This is a multi-layer system, and right in the middle is a monocrystal of rare earth barium copper oxide that is 1 to 3 micron thick and up to 1.4 kilometers long. Commercially, you can buy this tape in rolls that are about 300 meters long. 2 years ago, ARPA-E invested $10 million to stimulate the production of REBCO tape in America. The goal of the program is to multiply the length of the tape by a factor 2 and reduce the cost by a factor 10. We selected these 3 teams, and I encourage you to visit their booth today. Over the years, ARPA-E has invested in energy technologies that use REBCO tape. Some teams in fusion have explored different fusion reactor concepts. We are also investing in developing superconducting motors and superconducting cables for electric aviation. Here, the value of using REBCO tape is it can significantly reduce the weight of these components. As mentioned earlier, we are also interested in power transmission. In these different projects, our team have bought tape mostly from abroad, from Germany, Japan, South Korea, and not long ago from Russia. So these technologies of geostrategic importance, and we need to make sure that we can make the best tape here in America. So the question I have for all of you today is, what would you do with high-performance, low-cost superconductors? And if you allow me, I'd like to make a suggestion. We can use them in data centers. Here, just like in transmission, we can significantly reduce the footprint of the power delivery system. And we can get rid of transformers, converters, other power electronic devices that we currently use between the medium voltage and the IT load, which operates at 48 volts. So we can deliver a high amount of power at low voltage but high current. In all these applications, the adoption and deployment of superconducting energy systems rely on three pillars. First, we need low-cost, high-performance tape, but that's not enough. We need a cryogenic system that can keep this tape at temperature below their critical temperatures at all times. And we need to make sure that the system as a whole can be operated reliably and safely under all circumstances. When it comes to the cryogenic system, hotter is better. Currently, the superconducting systems that are deployed operate the tape at temperatures below 50 Kelvin. We need to take full advantage of the fact that these materials are high-temperature superconductors by increasing the operating temperature. Then we will increase the coefficient of performance of our cryogenic system. We will need only 2 temperature zones instead of 3, and maybe we'll be able to cool down the tape just by heat conduction, which will simplify and make the system more compact. Then it will be faster to cool down, and overall the cost will be cheaper. Now, some of you may think, we have the tape, we know how to make cryogenic systems operate over a wide range of temperatures. We've made superconducting magnets and other components, so what else do we need? And I would point, these systems have been developed independently of each other, because each of these components alone is already hard enough. But we have reached an inflection point, and now is the time to de-risk the system as a whole. How do we do this? We need to co-design the material, the cryogenic system, and other components for the purpose specifically of the system. We should use modular design to facilitate repair. The tape is often part of the structure of the system, and if it breaks, you got to be able to repair quickly. Same thing, we should use the design to make a fault-tolerant system for safety. Then we need to build the system. We do not need to build the biggest system ever. We should go small to go big faster. The system needs to be small so that we can build it cheaply and quickly, but large enough to be meaningful. And then we need to make sure that the manufacturing methods we use can be adapted and used for the small version or the larger version of the system. Then we need to test it. Not for a few hours, but for hundreds of hours under realistic conditions. And if it has not happened yet, we need to break the system. We need to make it fail so we can learn. Learn how it fails, learn the failing mechanism, validate models, and formulate technical solutions so we can go through this loop of design, build, test, learn several times, ideally within the time frame and the budget of an ARPA-E program. I believe this is what it will take to ensure that superconducting energy system will be adopted and deployed widely. So if you have ideas to support this vision, I'd love to talk to you tomorrow for coffee. And now, I will pass to Cory. Thank you.
Thanks, Dr. Pilon. Appreciate it. So that was pretty exciting. Superconductivity. I'm superconducted now. Thank you to do this as pitch. So it's exciting time, and I really believe that early stage researchers, the type that we fund here in ARPA-E now, they have the tools now to predict how your innovations will impact industrial process design, industrial process and chemical process design right now, really redefining, sort of reshaping, reimagining what's possible in industrial process design and process chemistry. So my name's Cory Phillips. I'm here to talk to you today about the secret agents that will usher in the next era of industrial process design. I'm going to spend about 8 minutes, maybe 9, 8, and I'm going to try to convince you that AI agents will really revolutionize the way we think about industrial process design and the way energy, R&D, and process technology can be conducted. Hopefully, someone out there will agree with me, and we'll talk, and you'll share with me your ideas. How about that? So, AI agents, agentic AI, it's been the buzzwords, it's been all over the news, it's all the rage. And it reminds me of the movie WALL-E. Now, WALL-E, you remember WALL-E, right? So WALL-E was the waste allocator, load lifter, for Earth. Oh, you don't remember that? Okay, well, that's what it was. He had a task. He had a specific task that WALL-E did, and he did it every day. He was set to do this task. And he had a friend, Evie. She was like the extraterrestrial vegetation evaluator. And so that's Evie right there. So they have these tasks that they're doing, and really they work together to save the world eventually. Agentic AI agents, very similar to this story in the sense that they're really autonomous software systems that are designed to perform tasks, make decisions, interact with their environment, learn, adapt, collaborate, work independently, all together really to just come and solve a problem, a tough problem that's really hard to do single-handedly. I don't know what that one's doing. Single-handedly do something. And they team up together and they solve these problems, much like the complex problems that we find in industrial, chemical, and process design. But what if we could take that power that AI agents have, collaborating, and put it in the hands of these researchers here in the room that we have, this power that could actually help them get out of the dark with where their early stage research is and put them into the position to actually have it commercialized while they're still in the lab. Considering all the enormity of considerations and complexities and design considerations early enough to where it's like giving them a crystal ball. And they can see into the future what their process looks like now in the lab at the early stage while they're still collecting data at very early TRLs. This is the power of generative AI working as AI agents. And I'm sure if you're a process engineer out here now, you can start brainstorming and thinking, or if you're just an early stage researcher, wow, this could really be powerful. I can figure out what I can do now while I'm in the lab and commercialize this. But it's really hard. It's a hard problem. And it's a hard problem because, it's a lot of issues associated with it with respect to the math and complexity. It's like an NP hard problem that they call in computer science. If you go and you prompt any commercial generative model that's popular, you ask it, hey, give me the Haber-Bosch process for ammonia synthesis. You might get something like that. And that is not a process flow diagram. But you probably wanted something like that. And it's a long ways away from that. But we want to get to the point where we start to put the groundwork and lay the groundwork to build out this kind of capability. And the reason why it's hard is that it's a complex problem. It's a complex problem in math. It's a hard math problem in the sense that you're trying to solve large arrays of discontinuous, complex, coupled, nonlinear arrays of data that have constraints to build out design criteria and working within mixed integer processing. Really tough problem, math problem. It's a hard process engineering problem. We have a dearth of process design engineers that are working at the commercial scale and really trying to have them, serve in these very incubation and early stage projects that deal with designing different units and units that may be more novel than they have worked with. That's tough as well. It's a hard risk problem. Managing the risk, asking questions and answering questions that we may not even know we're supposed to be asking. So we don't know what we don't know. Really trying to have agents and algorithms deal with that is almost impossible at this stage. And then it's a hard domain knowledge issue where extracting and encoding foundational knowledge from our subject matter experts, these paradigms, these rules of thumbs, the best practices involved in design, getting that into an algorithmic form where we can actually now train models and use it. It's really hard. So managing complexity is at the core of it. And when you look at process design and process engineering, there's so many permutations, so many opportunities. If I'm trying to get from A to B, there's all types of units, types of unit operations, unit equipment, there's stream configurations, there's different heat integration strategies, there's a lot of stream configurations. The design space becomes enormous really quickly. And so for professional design engineers, what they're trying to do is limit this space, because often they have to do the manual drawings and adjustments and modify these drawings every time there's a change. So they want to get inspired by things that work right now. You know, commercial processes that exist, and start there. It's actually like when you're dealing with the early stage researcher that's thinking about a commercialization, it's like solving a puzzle where you have like half the pieces available to you. So it's wonder if anything could ever really get out of the lab. But what if there's an opportunity for AI agents to simplify this complexity, simplify the complexity down to the point where as we get lab data rolling off, we can start getting inspired by commercial opportunities in process design. So those same commercial processes that we think about, they actually can be related to our data as it's evolving. So imagine you have go back to our case with ammonia synthesis, and I'm in the lab, and I get some lab results. You know, this is lab results that I took from literature that normalized reaction rates and this temperature and pressure data for different ammonia synthesis catalysts. And you have different conditions, and at each condition, say I might get inspired with a traditional Haber-Bosch process like this with my first attempt at my catalyst, and I said, okay, that's great. And so then I get another lab result, and it has different conditions on temperature and pressure and different reaction rates, but it also changes the configuration of the actual reactor. And then I get another lab result, and this lab result maybe has a different higher relative reaction rate, and it's a different catalyst, but it actually affects the way I do the recycle stream, all from my lab data. So my lab data is getting inspired or inspiring my process design. This would be different. This would be pretty unique, but there's still a lot of work to do. This is the commercial inspiration that begins the art of process synthesis. That's just the start. We still have to find all the metadata that's involved in taking lab data that, you know, this doesn't make it into the papers, it's in the notebooks, trapped somewhere, the little nuances and details. There's a lot of work involved in that. So we need agents. The question is, can we actually enlist these agents to actually do that work for us? And I think we can. I think we can have agents that actually extract data while it's evolving, and while that data is evolving, actually start generating the process flow diagrams, and then generating the equipment list, even your TEAs and your LCAs, actually even doing a little bit procurement scoping for you along the way, actually giving you ideas of what these drawings look like across multiple scales. And so you get several routes, and then they choose these routes based on the lab data. This is the future that we can have. And this is exciting. In fact, I'm going to coin the term generative evolutionary process synthesis. How about that? Because it's generative, but it's evolving because the data is evolving. And this would really revolutionize how we even train our process engineers, process design engineers. It can actually be in a case where the AI agents are also serving in an apprenticeship role, in a training role. And so if you're here and you're an early stage researcher, or you're a computer scientist, or you're a process simulation expert, process synthesis expert, and you share this vision, come check me out. Let's talk a little bit more about it. I think we'll have a lot of fun about the future of this evolutionary process synthesis. Thank you. And next, I'm going to pass it to my good friend, Dr. Chaban, who's going to tell you more about plasma processes in chemistry. Thank you.
Thank you, Cory. Now, Cory has an excellent idea about how to make our thermal processes better. But what if we rethink them entirely? I'm Ryan, and I'm a fellow at ARPA-E, and today I want to talk about how plasmas can do more than just fusion. Now, in our current world, fossil fuel heat is the cheapest form of energy, but it releases CO2. Meanwhile, electricity is much more expensive, but it doesn't have to release CO2. This means fundamentally, if we want to replace heat with electricity, we need to have massive gains in efficiency. At the end of this fast pitch, I hope you come away thinking that plasmas can be the route that we use to bring electrification to new sectors of the economy. This is for three main reasons. First, plasmas can be non-thermal. They can operate at room temperature and atmospheric pressure. Second, plasmas break scaling relations. They can be modular and decentralized, eliminating transportation costs and safety hazards. And third, most importantly, plasmas offer new pathways for single-step chemical reactions. Now, let's take a look at the scope of the problem we're facing. Every single one of the commodities on this table uses heat at some point in its manufacture. And I'm not talking about a little bit of heat. I'm talking boatloads of heat. Every single ton of commodity on here releases between 1 and 5 tons of CO2 during its manufacture. Now, if I want to use electricity to run some of these processes, it has been done before, right? Like with the electrochemical Hall-Héroult process for making aluminum. But it usually only happens when thermal alternatives are extremely tricky. So why not just use electricity to make the heat? Because electrons are absolutely terrible sledgehammers. Electrons are way too small to be good sledgehammers, right? We need to use so many of them. And if you want to use electricity as a fuel, that means it's going to be 5 to 10 times more expensive right off the bat. That's before you do all of the redesign for all of your CapEx, that half of it you have to throw out the window. So hold on, wasn't I talking about plasma? Right, so some of you may have noticed there's a pretty conspicuous white space in the upper left here. And that's because the highest production cost commodity that I can think of are semiconductors. And this is where plasma processes are the only place that you can make semiconductors, even though the volumes are small and the materials are pretty cheap, right? Semiconductors are just sand that we taught how to think. Now, what if but something that we gotta remember is that the fusion plasmas of 40 years ago are driving innovation at the edge of chip making today with extreme UV lithography. So can we learn from plasma chemistry and use it to drive the synthesis of other commodities? Now, before we go too far, what's a plasma? Right, so if we add heat to a solid, we get a liquid. If we add heat to a liquid, we get a gas. And if we add enough heat to a gas, we get a spicy, angry, ionized gas where we've ripped the electrons off of their molecules, and we call it a plasma. Now, what makes the chemistry with plasmas different? So, plasma chemistry, all chemistry, is fundamentally the rearranging of bonds to form different compounds. What we sometimes forget is these bonds, they're just electrons, right? Now, taking ammonia synthesis, like Cory briefly talked about, in the traditional thermal chemistry, we add heat and pressure, and this allows the nitrogens and hydrogens to bind with a catalyst, and then they come out as ammonia. It pushes us over the activation barrier. Now, with plasma, we can use high voltage electricity to slice these bonds in a much more specific way, and we create radicals and excited states. That dramatically reduces the energy required to move us over the activation barrier. This is all good in theory. Let's take a look at an example. 2 years ago, on this exact stage, my colleague Catherine Greco pointed out that industrial chemistry is full of unnecessary reduction oxidation steps. Every time we take a step on this scale, it costs energy and it costs complexity. Let's look at how plasma can make nitric acid, which is a common feedstock for fertilizers and semiconductor manufacturing, and turn it from a 3-step process to a one-shot. To make nitric acid, first we start by doing steam methane reformation to feed hydrogen to the Haber-Bosch process, which operates at extremely high temperatures and extremely high pressures. For every ton of ammonia that we make, we use 7.8 megawatt hours of energy, and we release 2.5 tons of CO2. Once we put all the energy into making this ammonia, then we partially oxidize it using the Ostwald process, where we have to put more energy in, even though the reaction itself is exothermic. Now, this operates at extremely large scales, on the order of 1,000 tons a day. That means that we have to do hazardous material transport to take it to our final point of use, and that increases the price by 20%. If we rethink this system with a plasma, running normal air through a dielectric barrier discharge can make NOx. NOx plus water in an absorption column makes single-step nitric acid. The whole process takes about 4 megawatt hours and operates economically at a scale of 1 to 5 tons a day. This means with plasma, we've gone 1/3 the energy with 1/3 the powered reaction steps, 10 times the yield per capex, and I've cut 20% off the price just by making you not have to put it on a truck. Now, this brings me to the main question I have for this audience. I want feedback. What other reactions and process chemistries can we use plasma for to increase the efficiency and reduce complexity? Now, with the time I have left, I want to talk about why ARPA-E, why now? The two technologies that I see that can make this field move forward. The first is high voltage power delivery systems, and the second is next generation reactors and co-design. Now, high voltage power delivery systems are getting much cheaper. Silicon carbide and gallium nitride are fast and they have higher standoff voltages, which means we can reduce the part complexity when we're making these high voltage systems. We can use these semiconductors in narrowband phased arrays where we can deposit microwave power exactly where we want the chemistry to happen. And we can use these semiconductors in pulse power systems that are dedicated to the chemistry we're trying to do. And we can sharpen these electrical scalpels to select the chemistry, and we can shape them so that we can get the chemistry to happen when we want it to happen. Now, plasma chemists over the past, long time have been perfecting the art of gas phase reactors. Thermal plasmas have traditionally struggled with mixing and quenching to prevent back reactions. But with modern tools like CFD, we can design these flows for the optimal chemistry. And non-thermal plasmas, both pulsed like dielectric barrier discharges and continuous like gliding arc discharges, have traditionally struggled, but now they're increasing the efficiency because we're making the electric fields more uniform and increasing the residence time so the chemistry can happen. But what about some wacky avant-garde ARPA-E ideas? There are groups out there upgrading methane to methanol, which is a critical feedstock at plasma liquid interfaces at room temperature and pressure. ARPA-E has ROSY performers who are using hydrogen plasmas to reduce iron ore to metal. And my personal favorite, high-temperature superconductors are becoming cheaper and more widely available, which means we can start to do magnetized plasma chemistry, where we can use these magnetic bottles and borrow what we have learned from the past 50 years of nuclear fusion research to confine, react, and even separate our products with more physics and less engineering. Now, from the sun to the aurora, from lightning to fusion, let's use new semiconductors and better reactor design to bring electrification to new sectors with plasma chemistry. If you want to be part of the team moving this white space forward, meet me at Coffee with ARPA-E and scan this QR code. Together, let's put lightning in a bottle. Thank you.
All right, so thank you for your attention. We'll take some questions from the audience. You can ask your question using the app. So I'd like to start first with Jeff. We already have some questions from the audience. Jeff, how long can permanent magnets last? How much more expensive are they compared to electromagnets?
Well, a permanent magnet is permanent. It lasts forever.
Okay.
Now, that being said, if you push back against it too much beyond its coercive force, then it needs to be reset. So you have to be gentle enough to your permanent magnet. And then how much do they cost? Well, that all depends on the materials and processing for the material. It doesn't need to cost too much. And for many applications, just a tiny little magnet will do what you need. So my program, I'm looking at cost is not a huge problem. because for many applications, it's worth it to have a stronger magnet.
Thank you. Cory, how do you consolidate and qualify the hundreds of data streams to make high-quality models?
How do I qualify it? How do I qualify it?
Qualify, yeah.
Oh,
qualify the hundreds of data streams.
Yeah, it's the first thing is actually acquiring that data. I think data acquisition I'm assuming the question is regarding developing the large data sets and pre-processing those to get them into a form to be modeled. So we're talking about a very tough problem. Once again, the computational computer science community would call this an NP-hard problem. And it's very difficult in the sense that there's different modes of attacking. I've sort of like had a very fun pitch, that kind of was very aspirational, but behind it is very grungy, dirty math that's very difficult. And you have to have this data set that enables you to get through different decisions. So, quickly, I say decisions, everybody goes, networks, networks, but it's even past that. We actually have to have a data set that enables us to envision process steps that may not be as obvious to those that are working in the industry as well, especially when you start looking at novel processing steps. So this is going to be challenging, and to actually first acquire the data and extract that data it have to come from multiple sources. It won't just be quantitative lab data. It's actually decision making and some what we would call foundational knowledge base.
Thank you, Cory. So Ryan, you mentioned reactor design and high voltage power supplies. What is the role of modeling if plasma chemistry moves forward?
We need modelers. Like I said at the end, plasmas exist over many orders of magnitude in time and space, arguably the most out of almost any field. And this means we need teams that have expertise all the way from density functional theory, if we're looking at plasma catalysis, and up through fluid dynamics and reactor and process flow design, because we have a lot of knowledge, like Cory said, about our thermal processes and how things might change there, but we have very little knowledge about how a plasma system, if you tweak it slightly, might change your recycling flows or your buffers or all of the other small unit operations. I know I had those flow diagrams up there, but that was only one step further than what ChatGPT would give you. They are still incredibly complex. And modelers are required at all levels to get the teams to work together.
Okay, thank you. One question for me, if you guys don't mind. Okay, so someone asked, how robust is the high temperature superconductors supply chain? Can it handle the demand from DC currents? Okay, so in terms of supply chain, it's not a problem. The main composition is YBCO. Yttrium is mined in the US. Barium is also available. So on the rare earth part and on the basic material part, we're fine. The challenge is how you make the tape and the cost of the tape. Right now, the tape runs between $100 and $300 per kiloamp meters, and that's really an obstacle to the adoption of the tape. And so that's why we had this program to reduce the cost by factor 10, to bring it down to $10. And that manufacturing capabilities is lacking in the US. We can do better, and that's why we need to do better. That's as far as the supply chain concern are. From handling the demand from DC, again, I think there's no demand for DC right now because it's too expensive. The demand right now is from fusion. That's the main demand. Okay. Jeff, a question for you. Is there a physical limit for magnetic properties of materials?
Well, most magnetism is due to unpaired spins per atom. And currently, iron is the best, has the highest magnetization with about 2 unpaired spins per atom. But we know other atoms have much higher. So manganese, for example, is normally in a high spin with 5 unpaired spins per atom. And gadolinium and other rare earth elements can be even more, 7 to 10. So the upper limit is probably 5 times what we have today.
Interesting. Thank you. Cory. Sorry.
No, pick a really easy.
Is there one particular industrial process or application that you favor as an initial proof of concept?
It's a good question because, you know, it's important when you're coming out with any new program or new initiative that you choose an application that gets everyone excited. And so I don't have any particular process, even though Ryan and I sort of ended up collaborating on the ammonia synthesis as an example, but that was just an example. Actually, the process synthesis industrial process can cross different industries. So for instance, right now, this year at Summit, we have our first cohort of the ROSI program, which are novel processes to make steel in novel ways, and iron, direct iron. So from novel feedstocks. And so I invite everybody to go down and check out the ROSI corner and all of those the processes there. So that would be examples of industrial process that we're trying to improve, and we're trying to get more energy around and actually helping out those performers because they need process synthesis and design for the early stage lab work. So it'd be great if, you know, I had this tool I could give to my ROSI performers. You know, that would be something I would love to do. But this in general, I think crossing different industries and different sectors. I showed the chemical industry, but easily it can go into other, you know, industries as well. There's a need for process design in other industries.
Thank you. Ryan, how do you anticipate to address challenges in scaling and safety in plasma reactors?
Good question. So the scaling of plasma is fundamentally different than the scaling of thermal reactors. Thermal reactors, they scale with volume, right? Plasma reactors actually have a huge advantage over their counterpart for electrification, which is electrochemical reactors, which scale with area. So plasma reactors can scale with volume, but in reality, the main limiting factor of the scaling is the power supply. So that's why I mentioned power supplies as being one of the main innovations that we need for this system. We need to have higher current densities and higher pressures. But you will never one-to-one replace a thermal reactor with a plasma reactor because the scale of a thermal reactor becomes economical at 1,000 tons a day, whereas plasma, the advantage is the modularity and the decentralization that you can have it anywhere and you can operate it at 1 to 5 tons a day. If you want 1,000 tons a day in one place because you have to, I guess you could put, you know, whatever 1,000 over 5 is 200 in the same place, but that seems not like a great idea.
Okay, thank you. Someone asked me, could you give some examples of how the design, build, test, learn cycle could play out? And here, I'd like to give an example of a superconducting motor, for example. For fusion, we need very high quality tape, but for motors, we don't need that quality. And so we could adjust the tape to the function. Also, so on the cryogenic system, we have developed cryogenic system that fits on the table that looks like a square. But that's not very easy to mount that cryogenic system on the rotor. So effectively for a motor, you want to have an axisymmetric cryogenic system, which does not exist. That system would have to sustain vibrations, very strong vibrations, which is a great challenge in the operation of the design of the motor. So this is where we can choose the right material, redesign the cryostat to adjust again for the purpose. And the testing, again, a small motor would help and really run it to the ground with a lot of vibrations that you would encounter in electric aviation, for example. This would be an example of this loop. Okay, Jeff, I think I saw a new one coming. What do you consider to be the most important and most achievable application of stronger magnets? What would be the first application or the most important?
Well, at ARPA-E, we're interested in energy. And so we're going to focus on massive power generation and use. And that means generators and motors. But in practicality, what's going to be the most important for energy? Probably the motors. Probably the motors and actuators where the size of the motor and the performance is most valuable. Because in reality, when we discover a new magnet, it's going to be made in a laboratory. We're going to be making it on the order of centimeters squared at a time, centimeters cubed at a time. And the beauty is that those materials, once tested, they could have the form which you could put right into a real application. So within a year, it's possible we could have a magnet that's so strong that you would want to put it in an earphone for a speaker, or you'd want to put it in a cell phone for communications. Now, for energy applications, maybe that means they're gonna solve some important application in aviation, right? There's high performance valves and motors and switches that all need magnets and need to fit into small little places. And so a smaller magnet could do that job better. And it's worth a lot more money to put in that small place. And so we could have a startup company that starts with these markets first. And then once we develop the processing techniques, then we can scale up for larger markets.
Thank you. Cory, the questions are, please keep sending them. We're getting a lot of them here. Cory, to solve the complex problem of process design, you may need data from physical experiments. Is there enough physical experiments available to train such complex models?
That's great comment, great question. Thank you so much. Yes and no. We know that for many of these generative model aspirations that we have to generate data. We have to generate data fast. So we already have some programmatic initiatives in ARPA-E where in the fields of materials and catalysis, we're trying to figure out how to do that data generation piece fast. But in terms of process design and process synthesis, the input would be lab data like I showed before, where you can imagine that you're kind of evolving the process design as you generate the lab data. Is it enough to actually start a large model? Probably not right now. So what I like about this question, I'm very interested in the person out there that gave that question to come up to me and chat with me about what do you think the techniques are to sort of allow us to get into that large data space, particularly for process design applications and generative process design. We know there's some teams in the Netherlands that are working on this. To the process synthesis community that may be in the audience, thank you first for coming, and I'm really glad you're here. I want to hear from you as well, and it's really time for us to get together and bring this to the forefront, because this is one of the elements in the Valley of Death or Mountains of Opportunity that really challenges teams that are developing technologies, and the data part of it, the amount of data, is at the core of the problem, one of the pieces of the problem.
And those people should come talk to me too, because I want to know what I'm not thinking about.
So Ryan, since you have the microphone, a question for you. Apparently we're receiving this question a lot about selectivity. Won't plasma chemistry give very low selectivities, and thus the benefits you get in process enthalpies is offset by cost in separation?
What an excellent question.
Yes, indeed.
Initially, yes. If we just take current plasma and we try and make industrial processes out of it, they won't work right now. This is why we need the sharper scalpels, like I was talking about. So if you look at the plots of the excited states that you're going to stimulate versus the reduced electric field that you have, if you have to be very precise with the electric field that you want. And actually, magnets are one way to be more selective about where you're creating the electric field. And the faster the rise time on a pulsed power type system, the more selective you can be with that chemistry. And I also agree for the separations part, a lot of our separations processes that we've developed over time are for thermal processes. They operate at large scales, they operate at either high temperature, they use temperature swing absorption, pressure swing absorption. So we need to operate plasmas at higher pressures and densities so we can start to use some of these traditional separations processes. Or there are, it's completely rethinking how we do the process design, and I'm not saying that's easy, but I think that a program in this area could absolutely bring the selectivity up to the level where we can start to think about using these plasmas, where we can actually start to use these plasmas for processes.
I like what Ryan did there, because he talked about operating plasmas at higher pressures and they have to be stable there. But what he was doing is actually doing a process synthesis step in his brain, his mind, actually designing the parameter to say, this is what I need to make this process happen. That's exactly what we want to do in process design, or at least agentic process design, is actually have those constraints available to us.
Okay, thank you very much. I have a question. A cheerleader of the HTS technology space, who wants me to remind everyone about the collective effort of this space, which is actually quite small. But the question is, and it's an easy one, so I'll take it. How can ARPA-E assist such a collective R&D effort and connect all players from conductors, cryogenics, and device designers and engineers? And in fact, that's exactly my point, is that these communities have been working in separate space. Cryogenic systems have been developed to achieve the maximum coefficient of performance without really thinking about where is it going to be used. Sometimes for an electric motor, we don't care whether it's working at maximum coefficient of performance. We want the maximum heat lift. And so, and bringing people together, that's what we actually do at ARPA-E. That's what the great aspect of ARPA-E is. We support teams. We don't support, we try to get people actually across the different disciplines to solve a problem and come up with a complete solution. So I think that justifies our existence and makes my point. Thank you. And then I think we're running out of time. So maybe we can get the music, or we have for another question. All right, thank you.
Thank you.
Thank you.